Hello everyone. So for my ESP project, I decided to do an in-depth analysis of the sextant. Ultimately, the goal of this project will be to understand the mechanism and the part behind the functioning of the sextant and to create my own replica of the sextant. My research was divided in different parts and I will present them. First of all, what is a sextant? So science has developed a number of tools to help us understand how space works. And around 1731, John Hadley invented one of them, the sextant, a machine used to calculate the angle between any given object and the horizon. In other words, latitude. And with the help of Harrison Marine chronometer, a device used to find longitude, the art of navigation reached unprecedented heights. And nowadays, it is obsolete due to our sophisticated satellite that can do the job faster and better. But the sextant was used for centuries to help human navigate throughout the sea and ocean. I decided to talk about this object because it reminds me of my grandfather and how we used to navigate together on his boat when I was a kid, and how he used to show me all of those cool instruments. So my project is primarily focused on the nautical sextant, which is the most known and used sextant, and the sextant that you can see in this slide. So there is different part of the sextant. The main one is the frame. It can be made of metal, plastic, or wood and acts to hold everything together. So it's all this thing that I point with my mouse. So on the frame, there is an index arm right there and a scale. Those two combined together are used to do the actual measurement. There are two mirrors on the sextant, the index mirror and the horizon mirror. So the index mirror is on the index arm and the horizon mirror is on the frame, and it is the horizon mirror is divided in two parts. At the right, it is a mirror, and at the left, it is actually see-through. Right, and at the opposite side of the horizon mirror, you can find the telescope, and it is perfectly lined up with this mirror so that you can see straight through it. And finally, last but not least, there is supposed to be two glass filters in front of the mirrors. So if you look a bright object, the sun, for example, it prevents you from burning your eyes. And it is believed that the fact that it didn't have glass filter is one of the reasons that many pirates and sailors wore an eye patch. So in this sextant, the along, so that's it. And so in the sextant, the angle along the scale corresponds to the angle between the object that you're looking at and the horizon. This is the sextant main principle, and it is based around the phenomenon of double reflection. So as we remember, and that we learned that in our optic class. So and it is at the top right figure. When ray of light hit a mirror, it is reflected, and there is two angles: the angle of incidence and the angle of reflection. Both of them are equal. So when you put two mirror in parallel, the four angle, so the two of incidence and the two of reflection, they're all isometric. But a strange phenomenon occurs when you rotate the second mirror. So in the case of the sextant, the horizon mirror. Oh, sorry. Yeah. So if you rotate the second mirror by an angle x, it will add x to the incidence mirror and to the incidence angle and to the reflection angle. So at the end, the final angle, there will be 2x added. For example, if you rotate your second angle in the sextant by 30 degrees, the final measurement of the scale, there will be 60 degrees more. And this is known as the double reflection principle. So here you can see it too. So the sun, the ray of light from the sun hit the first mirror, then the second mirror. So there is two main utilization from the sextant. The first one is with the angular size formula that we learned in class previously. So we remember that with the sextant, you can calculate the angle between the horizon and an object. And if you know the height of the object or the distance between you and this object, you can just plug them in the formula to find the third measurement missing. The second utilization of the sextant is to find latitude. So we also learned latitude in class. And for this, you just have to find the angle between you and Polaris with the sextant. So for example, you know that if you are on the top, on the North Pole, you're at latitude 90° north. And if you are in the hemisphere north, and you will look at Polaris with your sextant, it will do like a straight line, so an angle of 0°. So to find your latitude, you do 90 minus the angle that you find with Polaris. So in this case, 90 minus 0, and this would be 90. And if you are straight at the equator, looking at Polaris, there will be a 90° angle between Polaris and the equator, and 90 minus 90, it's 0. And you know that the latitude at the equator is 0. So it works. So one of the constraints for the ESP project was that it must involve knowledge from another science discipline. And Sextant involved knowledge from physics because of it involved optics and angular distance, which are both part of physics they are both branch of physics. And for mathematics, it includes trigonometry and a lot of mathematical concepts. If you want to find, for example, the dip of a reason, well, the dip of a reason is something that you want to find if you want to subtract it to the angle measure with your sextant, because if you are on top of the horizon, I'll show it with my mouse. There is an angle which is you don't want it. You want to subtract it. It is en trop. And the calculation to find the formula to determine this angle, or you have to derive for other formulas, and it's much complex. So I'll just show you. So you remember that one of my goal was to create my own sextant, so that I could find my latitude, for example. So I did it, and I will show it to you right now.
Hello everyone, here I am with the sextant I created. So obviously it's not a nautical sextant because it don't have the mirrors, and I don't have the woodcrafting skills to carve one. But it worked just as well to find the latitude and an angle between me and a given object and with the horizon. And it's called a chronometer, which is a type of sextant. So it's still a sextant. And to build it, first you need paper, like solid paper, and with a protractor, you can write angle between 0 and 90. So the angle that interests us, from 0 to 90. And on top of it, I put a straw to locate the top of the building, or, for example, for your latitude and North Star. And also there's a fishing line connected to a mast, and while looking at your object, the fishing line, you have to wait till it's stabilized, and it will tell you exactly the angle between your object and your horizon. So we can try it. For example, a more practical example. We will find our latitude. So I'll go outside. If you want to find your latitude, first you have to locate Polaris, which is the North Star, all the way on the north. And you can see the Big Dipper and the two stars at the bottom. You follow them and they will point towards Polaris, which is, yes, I will find it now with my straw. It's kind of difficult because the sky is big. I got it. So I'll have to wait till my stool stabilizes. And here we stop. So I have the angle between, and if you can see here, the angle, it's 54 degrees. So yeah, 54 degrees. So this means that the latitude that I found with my clinometer is 90 minus 54, as I explained before. So that's 46 degrees, and we can compare it with the latitude of Montreal to see if my calculation were correct. And I don't have the latitude of Montreal now, but I will tell you soon, in 2 seconds.
Thank you, Marco. I'll take it from there. So yeah, I went to Stellarium to find the latitude of Montreal, and it was actually 45 degrees and 18 arc minutes. So it's pretty close to what I found with my Sextant, which is a proof that, well, it works. And in conclusion, I only encourage you to continue the research about Sextant by yourself, because it's a topic really vast and captivating. Yeah, thank you for your time and attention. And here is my bibliography.